Now, in this lecture, we find out the size of the shaded area. In the drawing, we have a circle that is inside this quarter circle. In addition, we know that the radius of this circle r equals to the square root of 2 units. And our mission is to find out the size of this shaded area or the size of the green area. Okay, so first of all, we define the names of the relevant points to this question. That is to say, we define this point as A, we define this point as B, we define the center of this quarter circle, this point as O, we define this point as C, we define this point as D, we define the touching point between the circle and the quarter circle as E, and finally we define the center of this circle, this point, as F. In the next step, we join points F and C together by a straight line. What is the definition of line segment FC? Point F is the center of this circle, point C is the point of the circle itself. This is exactly the definition of a radius. Therefore, FC is the radius of this circle that is equals to the square root of 2 units in its length according to what is given as the question. So FC equals to the square root of 2. Here we can implement rule 1. I'll remind you quickly what is rule 1. According to rule 1, a tangent to the circle is perpendicular to the radius drawn to its point of tendency. In the drawing we have a circle and we have also tangent AB. This is tangent AB that is tangent to this circle at this point, point M. Point M is the point of tendency, and we also have the radius OM that is drawn to point M, that is the point of tendency of tangent AB with this circle. And whenever you have a radius that is drawn to the point of tendency, then tangent AB will be perpendicular to the radius MO. If AB is perpendicular to MO, it means that this angle equals to 90 degrees and this angle equals to 90 degrees. We can actually implement this rule 1 in our drawing. Why? Because in our drawing we have the radius FC that is drawn to point C, that is the point of tendency of tangent OD with this circle. And whenever you have a radius that is drawn to the point of tendency, then tangent OD will be perpendicular to the radius CF. If OD is perpendicular to CF, it means that this angle equals to 90 degrees. And this angle also equals to 90 degrees according to rule 1, of course. Likewise, we have the radius FB that is equal to the square root of 2 units. The radius FB is drawn to point B, that is the point of tendency of tangent AD with this circle. And whenever you have a radius that is drawn to the point of tendency, then tangent AD will be perpendicular to the radius BF. If AD is perpendicular to BF, it means that this angle equals to 90 degrees and this angle also equals to 90 degrees according to rule 1. In the next step, we'll focus on this quadrilateral BFOC. Inside this quadrilateral BFOC, we have 1, 2, 3 right angles. The sum of 3 right angles is 270 degrees plus the size of this fourth angle. In total, the sum of those 4 angles must be equal to 360 degrees according to the rule that the sum of the angles in any quadrilateral is equal to 360 degrees. Therefore, the missing angle must be equal to 90 degrees in its size. Again, in order to complete the sum of the angles inside this quadrilateral BFOC to 360 degrees, the missing angle must be equal to 90 degrees in its size. So actually found out that inside this small quadrilateral BFOC, we have 4 right angles, and we know that any quadrilateral that has 4 right angles must be at least a rectangle if not a square. So we relate to this quadrilateral BFOC is a rectangle. And we also know that the opposite sides of a rectangle are equal to each other. That is to say, BF, side BF, must be equal to the opposite side OC in rectangle BFOC. BF equals to OC. But BF equals to the square root of 2 units. Therefore, OC must be also equal to the square root of 2 units in its length. Likewise, according to the same rule, in rectangle BFOC, side FC must be equal to the opposite side BO. FC must be equal to the opposite side BO. But FC equals to the square root of 2 units, therefore BO must be also equal to the square root of 2 units in its length. So after we found out that quadrilateral BFOC, this small quadrilateral, is not a rectangle but a square. Why? Because all of its sides are equal to each other. Each side of this square is equal to the square root of 2 units. Okay, so in the next step, we'll join points O and F together by a straight line. By joining points O and F, we can add here 2 right triangles that are also an isosceles triangle. Why? Because those 2 sides are equal to each other. So, in the right and isosceles triangle, OBF, those 2 sides are equal to each other, and we have the rule that in front of equal sides in the triangle there are equal angles. So those 2 angles that are located in front of those 2 equal sides must be equal to each other. So if we define the length of the size of this angle is alpha, then the other angle must be also equal to alpha because they are equal to each other. And we also know that the sum of the angles in any triangle is equal to 180 degrees. So the sum of the angles in this triangle OBF must be equal to 180 degrees. So which angles we have inside this triangle OBF? We have this is a right angle that is equal to 90 degrees in its size, plus this angle that is alpha, plus this angle that is also alpha. In total, they must be equal to 180 degrees according to the rule that the sum of the angles in any triangle is equal to 180 degrees. So we actually found out that inside the right and the isosceles triangle OBF, the sum of the angles equals to 180 degrees, so 90 degrees plus alpha must be equal to 180 degrees, so 90 degrees plus 2 alpha must be equal to 180 degrees. Here we subtract 90 degrees from this equation, and finally we will get that 2 alpha equals to 180 degrees minus 90 degrees, this is 90 degrees. Here we divide this equation by 2, and finally we get that the size of angle alpha is 90 degrees over 2 is 45 degrees. Okay, so angle alpha equals to 45 degrees in its size. This is angle alpha that is equal to 45 degrees. and this is also angle alpha, that is equals to 45 degrees in its size. In the next step, we'll implement the Pythagoras theorem on this right and isosceles triangle, triangle OCF. In the right and isosceles triangle, triangle OCF, according to the Pythagoras theorem, in any right triangle, the square of the hypotenuse equals to the sum of the squares of the perpendiculars. So inside this right triangle OCF, in this right triangle OCF, the hypotenuse is OF, therefore the square of the hypotenuse is OF squared. That is equals to CF squared plus CO squared. Repeat again. In the right and isosceles triangle, triangle COF or OCF, according to the Pythagoras theorem, OF squared equals to CF squared plus CO squared. So OF squared, that is the square of the hypotenuse, equals to CF squared. CF is square root of 2, therefore CF squared is square root of 2 squared, that is 2, plus CO squared. CO is also 2, so CO squared is 2 squared, that is 2. So in conclusion, found out that OF squared, that is the square of the hypotenuse in the right and the isosceles triangle, triangle OCF, equals to 2 plus 2, that is 4. So OF squared equals to 4. Here we take a root out of this equation, and finally we get that OF equals to the square root of 4, that is 2. So here the hypotenuse OF is equals to 2 units in its length. In the next step, we will extend the hypotenuse OF, or we'll extend the segment OF by a straight line. But before that, I will present to you rule 9. According to rule 9, if two circles touch each other internally, then the straight line that connects their centers together passes through their touching point. So in the drawing we have two circles. They have an internal notch between them, that is to say, they touch each other internally at this point, point P. Point P is their touching point, or point P is their point of tendency. The center of the big circle is here at point O, the center of the small circle is here at point M, as the straight line, and the straight line that connects their centers together is the straight line OM. And according to this rule, rule 9, the straight line OM that connects their centers together must pass through their touching point, that is actually point P. Or OMP is one straight line. OMP is one straight line. Or we can say also that the 3 points O, N, and P that are all located on the same straight line. Or OMP is one straight line. Okay? So we can actually implement rule 9 in our drawing. Why? Because in our drawing, we know that the center of the quarter circle is here at point O, and the center of this small circle is here at point F. The straight line that connects their center together is the straight line OF. And according to rule 9, We have here, before that we have here the circle and the quarter circle have an internal notch between them. That is to say they touch each other internally here at this point E. And whenever you have an internal notch between two circles, you can implement rule 9. Therefore, you can implement in this drawing, in our drawing, rule 9. According to rule 9, the straight line that connects their centers together, that is to say the straight line OF, must pass through their touching point. Their touching point is here at point E. So the straight line OF must pass through point E, that is to say OFE is one straight line. OFE is one straight line. So we'll extend the straight line OF, and according to rule 9, the straight line OF must pass through point E. That is to say OFE is one straight line. Okay. What is the definition of line segment FE? Point F is the center of the circle, point E is the point on the circle itself. This is exactly the definition of a radius. So FE is the radius of this circle. This equals to the square root of 2 units in its length according to what is given us the question. So FE equals to the square root of 2 units, and we have already found out that OF equals to 2 units. And according to rule 9, OFE is one straight line. If OFE is one straight line, then OFE must be the radius of the quarter circle, because it is a one straight line. Why OFE is the radius of the quarter circle? Because point O is the center of the quarter circle. Point E is a point on the quarter circle itself. This is exactly the definition of a radius. So OFE is the radius of the circle, of the quarter circle. So we define the radius of the quarter circle as capital R. So capital R is the radius of the quarter circle, and capital R equals to OFE. OFE, the length of line segment OFE equals to OF plus FE. OFE equals to OF plus FE. So OFE equals to OF, that is 2, plus FE, that is square root of 2. So in total, OF equals to 2 plus square root of 2. That is to say, the radius of this quarter circle capital R equals to 2 plus square root of 2 units. Okay. We will define the intersection point of line segment OF with this small circle as H. If OFE is one straight line, it is actually the radius of the quarter circle. It is also one straight line. If OFE is one straight line, it means that HFE, that is part of OFE, must be also a straight line. Okay, again, according to rule 9, OFE is one straight line. If OFE is one straight line, then HFE, that is also part, it is part of OFE. HFE is part of OFE, therefore HFE must be also a straight line. So HFE is a straight line, but HFE is a straight line that touches the circle, the small circle here at point H, and at point E. So any straight line that touches the circle at 2 points must be a chord. So OFE is a chord, but OFE is a chord that passes through point F. Any chord that passes through the center of the circle must be the diameter of the circle. Point F is the diameter, is the center of the circle, and we know that any chord that passes through the center of the circle must be the diameter of the circle. Therefore, chord FE, chord edge FE that passes through the center of this circle, that is to say from point F, must be the diameter of this circle. So edge FE is the diameter of the circle. I want it now. Edge FE, line segment edge FE, is the diameter of the circle. Diameter of the small circle. And we also know that any diameter of any circle bisects the circle into two equal areas, to two halves. So the diameter edge phi bisects this small circle into two halves. This is the first half, and this is also the second half. So therefore, this is a semicircle, and this is also a semicircle. So in conclusion, we can conclude that this is a semicircle. Okay? So I can write down that edge BE is a semicircle. Edge BE is a semicircle. This is a semicircle. And our mission is to find out the size of this shaded area or the size of this green area. So what is the size of the green area? From the drawing, it is very easy to see that the size of this green area is equals to the size of sector AOE. This is sector AOE. Minus the size of this semicircle, the small semicircle, and minus this shape BO edge, minus the orange shape BOH. Repeat again. The area of this green shape, or the area of this shaded, or the size of this green shape, or the size of the shaded area is equals to the area of this sector, sector AOE, minus the area of this semicircle, minus the area of this orange shape. Okay? Again, the size of the shaded area is equal to the area of sector AOE. Here, the sign above AOE is the sign for the area of a sector. It means that this is AOE is a sector. This is the sign for a sector. So the value of the shaded area equals to the area of sector AOE minus the area of the small semicircle minus the area of the orange shape BOH. Okay. So what is the definition of a sector? Here, the green shape is sector AOB. And sector AOB consists of two legs. AO is the first leg, BO is the second leg. Both legs are the radii of this circle that is equal to R. And the angle between the two legs, this angle equals to theta. So you can see a sector as a slice of a cake. If a cake is a circle, then a sector is a slice of a cake. Okay. So the area of this sector AOB equals to the area of the circle that is pi r squared times theta over 360 degrees. Okay. Again, the area of this sector AOB, so this is the sign of the area. This is the area of sector AOB is equals to pi r squared, that is the area of the circle, times theta over 360 degrees. Theta is the angle between the legs of sector AOB. Okay, you can actually implement the new rule in order to find out the area of this sector, sector AOB. So what is the area of sector AOB? AOE, this is sector AOE. What is the area of sector AOE? The area of sector AOE equals to the area of the big circle, that is actually pi times capital R squared, times the angle between the legs of this sector AOE. This is the angle between the legs AOE, AO and OE is equals to 45 degrees. This angle equals to 45 degrees and inside, so it is 45 degrees over 360 degrees. So in conclusion, we found out that the area of the big sector AOE, in total, the area of the big sector AOE equals to pi times capital R squared, that is the area of the big circle, times 45 degrees over 360 degrees. 45 degrees is the angle between the legs of sector AOE. This angle equals to 45 degrees in its size. So we have already found out that capital R equals to 2 plus square root of 2. So the area of the big sector AOE equals to pi times capital R squared. R equals to 2 plus square root of 2. If R equals to 2 plus square root of 2, it means that R squared equals to 2 plus square root of 2 squared times 45 degrees over 360 degrees. 45 degrees over 360 degrees is 1/8 or 1/8. So we have to divide it by 8. So we found out that the area of sector, the big sector AOE is equals to pi, and we have here 2 plus square root of 2 squared is equals to 2 squared, that is 4, plus square root of 2 squared, that is 2, plus 2 times 2 times square root of 2, and you have to divide it by 8. So it is pi, inside the brackets we have 4 plus 2, that is 6, plus 2 times 2 is 4, so in total this expression in the numerator is equals to 4 times square root of 2 divided by 8. Here we will divide both the numerator and the denominator of this expression by 2, and we get that the area of the big sector AOE is equals to pi, and inside the brackets we have 6, 6 over 2 is 3, plus 4 times square root of 2. 4 times square root of 2 over 2 is 2 times square root of 2. Divided by 8. We have to divide also the denominator 8 by 2. 8 over 2 is 4. So in conclusion, found out that the area of the big sector AOE, that is part of the big circle, of course, is equal to pi, inside the brackets we have 3, plus 2 times square root of 2 over 4 square units. In the next step we have to find out the area of the semicircle. What is the area of this small semicircle? We know that the radius of this small semicircle is r, and therefore the area of the small semicircle will be equal to pi r squared, that is the area of the circle, over 2. It is given us the question that r equals to the square root of 2 units. If r equals to the square root of 2 units, it means that r squared equals to the square root of 2 squared divided by 2. So the area of the semicircle equals to pi, and square root of 2 times 2, square root of 2 times 2 is 2, divided by 2. 2 over 2 is 1, so here we left only with pi. In conclusion, found out that the area of the semicircle is equals to the area of the small semicircle is equals to pi square units. Pi square units. In the next step, we find out the area of this orange shape. What is the area of the orange shape? B edge O. What is the area of the orange shape? B edge O. The area of the orange shape B edge O is equal to the area of triangle BFO minus the area of the small sector BFH. This small sector BFH. again. The area of the orange shape BHO, it is equals to the area of the right-hand isosceles triangle BFO minus the area of the small sector of the small circle BFH. So the area of the orange shape BHO equals to the area of this right-hand isosceles triangle BOF. The area of any triangle is equals to the base of the triangle times the height to the base over 2. So the base will be square root of 2 times the height to the base is also square root of 2 divided by 2. So the area of triangle BFO equals to square root of 2 times square root of 2 over 2. Square root of 2 times square root of 2 is 2 and 2 over 2 is 1. So in conclusion we found out that the area of the right-hand isosceles triangle BFO equals to 1 square unit, and we have to subtract from the area of triangle BFO the area of the small sector BFH. So the area of the small sector BFH, we know that the area of any sector equals to the area of the circle, that is pi r squared, times the angle, this is sector BFH, the angle between the legs of this sector BFH, this angle equals to 45 degrees in size, so it is 45 degrees over 360 degrees. Repeat again, the area of the small sector BFH equals to pi r squared, that is the area of the small circle, times 45 degrees over 360 degrees. Again, 45 degrees is the angle between the legs of the small sector BFH. So it is pi, r is square root of 2, therefore r squared is square root of 2 squared, and 45 degrees over 360 degrees, it is 1 over 8. So it is pi, and square root of 2 squared is 2 over 8. Here we divide both the numerator and the denominator of this expression by 2, and get that 2 pi over 2 is pi, and in the denominator we have 8, 8 over 2 is 4. So in conclusion, we found out that the area of the small sector BFH equals to pi over 4 square units. So in total, the area of the orange shape BHO equals to the area of triangle BFO, that is 1, minus the area of the small sector BFH, that is pi over 4. So in total, the area of the orange shape BHO, it is equals to 1 minus pi over 4 square units. So we found out the area of sector AOB, we found out the area of the small semicircle, and we found out the area of the small orange shape BHO. Now, the only thing that is left to do is to put the data inside the formula for the area of the green shape, or the value of the size of the shaded area, the size of the green shape, will be equal to the area of the big sector AOE, that is also is actually equals to pi times 3 plus 2 times square root of 2 over 4 square units minus the area of the semicircle is equals to pi square units minus the area of the orange shape BHO that is equals to 1 minus pi over 4 square units. Repeat again. The size of the shaded area equals to the area of the big sector AOE minus the area of the semicircle minus the area of the orange small shape BHO. Okay. So here we'll open the brackets and we get that the size of the green area in total will be equal to pi 3 plus 2 times square root of 2 over 4 minus pi, we'll open the brackets here it will be minus 1, minus times minus is plus, so it is plus pi over 4. So the size of the shaded area will be equal to pi times 3 plus 2 times square root of 2 over 4, and here we have minus pi plus pi over 4 is minus 3/4 pi minus 1. Here we'll open the brackets of this expression and we get that pi times 3 is 3 pi plus 2 times square root of 2 times pi over 4, and we have also here minus 3 pi over 4 minus 1. Here we multiply minus 1 by 4 and then we divide it by 4 in order to account factor with the other two expressions. Minus 1 times minus 4 is minus 4 divided by 4. In this expression we have 3 pi minus 3 pi that is 0, so those two expressions will get cancelled and we left only with 2 times square root of 2 times pi minus 4 over 4. Here we divide both the numerator and the denominator of this expression by 2 and we get that 2 times square root of 2 times pi over 2 is square root of 2 times pi minus 4 over 2 is minus 2 divided by, we have to divide also the denominator 4 by 2, so 4 over 2 is 2. So in conclusion found out that the size of the green shape or the middle of this shaded area it is equals to either the square root of 2 times pi minus 2 over 2 square units, or in terms of numbers the size of this green shape is equals to 1.2214 square units. And that is the answer to the question. In the next step, I will summarize the lecture. In this lecture we found out the area of this green shape in the drawing we have a circle that is inside this quarter circle, and we know that the radius of this small circle r equals to the square root of 2 units. Again, our mission is to find out the size of this green shape. So first of all, we define names, or we define the relevant points of this question. We define this point as A, we define this point as B. This is the center of the quarter circle that we defined as O. We define this point as C, we define this point as D. And this is the point of tendency of the small circle with the quarter circle. We define the point of tendency as E. Then we join points F and C, and finally we defined the center of the circle, this point, as F. Then we join points F and C together by a straight line. What is the definition of FC? Line segment FC. Point F is the center of the small circle, point C is the point of the small circle itself, therefore FC is the radius of this small circle, that is equal to the square root of 2 units in its length, according to what is given as the question. So the radius FC is drawn to point C, that is the point of tendency obtained at OD with this circle. And whenever you have a radius that is drawn to the point of tendency, then tangent OD will be perpendicular to the radius CF. So if OD is perpendicular to CF, it means that this angle equals to 90 degrees, and this angle also equals to 90 degrees according to rule 1. FB is the radius of this circle that equals to the square root of 2 units in its length. Again, we have the radius FB that is drawn to point B, that is the point of tendency obtained at AO with this small circle. And whenever you have a radius that is drawn to the point of tendency, then tangent AO will be perpendicular to the radius BF. If AO is perpendicular to O and BF, it means that this angle equals to 90 degrees, and this angle also equals to 90 degrees according to rule 1. So inside this small quadrilateral BFOC, we have 1, 2, 3 right angles. The sum of 3 right angles is 270 degrees, plus the size of the fourth angle. In total, they must be equal to 360 degrees, according to the rule that the sum of the angles in any quadrilateral is equal to 360 degrees. Therefore, the missing fourth angle here must be equal to 90 degrees in its size. In order to complete the sum of the angles inside this quadrilateral BFOC to 360 degrees, the missing angle must be equal to 90 degrees in its size. So inside quadrilateral BFOC, we have 4 right angles. Any quadrilateral that has 4 right angles must be at least a rectangle, if not a square. So we relate to this small quadrilateral BFOC as a rectangle. And we also know that the opposite sides of a rectangle are equal to each other. That is to say, side BF must be equal to the opposite side OC in rectangle BFOC. But BF equals to the square root of 2, therefore OC must be also equal to the square root of 2 units in its length. Likewise, according to the sum rule, side FC must be equal to the opposite side BO in rectangle BFOC. But FC equals to the square root of 2 units. It is the radius of this small circle. Therefore, BO must be also equal to the square root of 2 units in its length. Actually, we found out that quadrilateral BFOC is not a rectangle but a square. Why? Because all of its sides are equal to each other. Each side equals to the square root of 2 units in its length. Then, in the next step, we join points F and O together by a straight line. By doing this, by joining points F and O, we created here those 2 right and associated triangles that the square is consists of. So if you focus on this right triangle OFB, in the right triangle OFB, it is also associated triangle. Those 2 sides are equal to each other. Each side equals to the square root of 2 units, therefore they are equal to each other. And we have the rule that in front of equal sides in the triangle there are equal angles. So those two angles that are located in front of those two equal sides must be equal to each other. So if this angle is alpha, then the other angle must be also equal to alpha because they are equal to each other. And we also note that the sum of the angles in any triangle is equal to 180 degrees. So which angles do we have inside the right and associated triangle, triangle FBO? We have this angle that is 90 degrees plus this angle that is alpha plus the other angle that is also alpha. So if I'm going to find out that in the right and the associated triangle, triangle OBF, 90 degrees plus alpha equals to 180 degrees. 90 degrees plus alpha is 2 alpha. This equals to 180 degrees. Here we subtract 90 degrees from this equation. We find out that 2 alpha equals to 180 degrees minus 90 degrees. It is equals to 90 degrees. So 2 alpha equals to 90 degrees. We divided this equation by 2 and finally found out that alpha equals to 45 degrees in its size. This is angle alpha that is equal to 45 degrees, and this is also angle alpha that is equal to 45 degrees in its size. In the next step, we implemented the Pythagoras theorem on this right and associated triangle, triangle FOC. According to the Pythagoras theorem, in any right triangle, the square of the hypotenuse equals to the sum of the squares of the perpendiculars. The hypotenuse in the right triangle FOC is FO, therefore the square of the hypotenuse is FO square, then it must be equal to FC square plus CO square. Repeat again, in the right and associated triangle, triangle OCF, OF square must be equal to CF square plus CO square. So OF square, that is the square of the hypotenuse, must be equal to CF square. CF is square root of 2, therefore CF square is square root of 2 squared, that is 2, plus CO square. CO is also square root of 2, therefore CO square is square root of 2 squared, that is 2. So in conclusion, we found out that OF square equals to 2 plus 2, that is 4. OF square equals to 4. Here we took out of this equation and finally found out that OF equals to the square root of 4, that is 2. So the length of line segment OF is 2 units. Then I presented to you rule 9, and I presented rule 9 in our drawing. According to rule 9, if two circles touch each other internally, then the straight line that connects their centers together must pass through their touching point. The center of this big circle is here at point O, the center of this small circle is here at point M, and the straight line that connects their centers together is the straight line OM. And according to this rule 9, the straight line OM must pass through their touching point, it's actually point P. Or OMP is one straight line. Again, OMP is one straight line. So we can actually implement rule 9 in our drawing. Why? Because in our drawing, the center of this small circle is here at point F. The center of the big quarter circle is here at point O. And the straight line that connects their centers together is line segment OF, or the straight line OF. And according to rule 9, first of all, here we have an internal notch between the small circle and this quarter circle. That is to say, they are touching each other internally here at point E. Whenever you have an internal notch between two circles, you can implement rule number 9. Therefore, you can implement here rule 9. And according to rule 9, the straight line that connects their centers together, that is to say, the straight line OF must pass through point E, or OFE is one straight line. OFE is one straight line. So here we know that point F is the center of the small circle, point E is a point on the circle itself, therefore OFE, FE, line segment FE is the radius of this small circle that is equal to the square root of 2 units according to what is given us in the question. And we have already found out that FO equals to 2 units in its length, And according to rule 9, OFE is one straight line. If OFE is one straight line, it means that OFE is also actually the radius of the quarter circle. Why? Because point O is the center of the quarter circle, point E is the point of the quarter circle itself, therefore OE is the radius of the quarter circle. We define the radius of the quarter circle as capital R, therefore OFE equals to capital R, that is the radius of the quarter circle. What is, if OFE is one straight line according to rule 9, it means that OFE in total, the length of OFE in total will be equal to OF plus FE. Again, OF equals to OF plus FE because OFE is one straight line. So OFE in total will be equal to OF, that is 2, plus FE, that is square root of 2. So in total OFE equals to 2 plus square root of 2. OFE is the radius of the quarter circle, therefore the radius of the quarter circle equals to OFE, that equals to 2 plus square root of 2. In conclusion, note that the radius of the quarter circle capital R equals to 2 plus square root of 2. Okay, we know that according to rule 9, OFE is one straight line. If OFE is one straight line, here HFE must be also one straight line, because HFE is part of OFE, and OFE is one straight line, therefore HFE, that is part of OFE, must be also a straight line. So HFE is a straight line. HFE is a straight line that touches the circle 2 points, at point E and at point H. So HFE must be a chord because it touches the circle at 2 points and it is a straight line. This is the definition of a chord. So HE is a chord, or HFE is a chord, but it is a chord that passes through point F, that is the center of this small circle. And any chord that passes through the center of a circle must be the diameter of a circle. Therefore, HFE is the diameter of the circle. If HFE is the diameter of the circle, it means that HE is also the diameter of the circle. So HE is the diameter of this small circle, and we know that any diameter of any circle bisects the circle into 2 halves. This is the first half, that is the semicircle, and this is the second half, that is also a semicircle. In conclusion, we can write down that HBO is a semicircle, because the diameter bisects the circle into 2 equal areas. Each area is defined as a semicircle. This is a semicircle, and this is also a semicircle. In conclusion, you can write down that this is the shape HBO is a semicircle. Okay? So we know that HBO is a semicircle, and we know that what is the definition of this shape AOE? What is the definition of shape AOE? Actually, shape AOE, this shape AOE is a sector of the quarter circle, or is a sector of the big circle. That the quarter circle is part of it. And a sector is a part of a circle. Here you can see the green shape AOB is sector AOB. A sector is like a slice of a cake. If the circle is a cake, then the sector is a slice of a cake. Okay? So AOB is a sector. The sector consists of 2 legs. The first leg is AO and the second leg is BO. And the angle between the legs of this sector is theta. and the two legs of this sector is the area of this circle that is equal to R. So the area of this sector AOB, there's actually the green shape, will be equal to pi r squared, that is the area of the circle, times theta over 360 degrees. Theta is the angle between the legs of this sector. Okay, so AOB is a sector, and the area of this sector AOB equals to pi r squared times theta over 360 degrees. Again, theta is the angle between the legs of the sector. So actually, therefore AOE, the shape AOE is also a sector of the big circle. We know that the angle between the legs of this sector, this angle equals to 45 degrees. This sector have those two legs, leg AOE, leg AO, and leg EO. Those two legs are part of this sector AOE. AO is radius of the big circle that is equal to capital R, and EO is also the radius of the big circle that is equal to capital R. Therefore, the area of this sector will be equal to pi times capital R squared times theta over 360 degrees. Theta equals to 45 degrees. So in total, the area of this sector AOE will be equal to pi times capital R squared times 45 degrees over 360 degrees. Okay, and our mission is to find out the size of this green shape. What is the size of this green shape? So on the domains it's very easy to see that the size of this green shape equals to the area of sector AOE, this big sector AOE, minus the area of this small semicircle, minus the area of this orange shape, HBO. Repeat again. The value of the shaded area in total equals to the area of the big sector AOE minus the area of the small semicircle minus the area of the orange small shape BHO or BOH. And as I already explained to you, the area of sector AOE will be equal to pi times capital R squared times 45 degrees over 360 degrees. We have already found out that here OE equals to the radius of the big circle, that's a capital R, and OE equals to OF plus FE. That is to say, O equals to OF, that is 2, plus FE, that is square root of 2. So in total, O equals to 2 plus square root of 2, that is actually the radius of the quarter circle that is equal to capital R. So in conclusion, we found out that capital R equals to 2 plus square root of 2. And the area of sector AOE equals to pi times capital R squared times 45 degrees over 360 degrees. So pi times capital R squared. Capital R equals to 2 plus square root of 2, therefore capital R squared equals to 2 plus square root of 2 squared. And 45 degrees over 360 degrees is 1/8 or 1/8. So we have to divide it by 8. So we have the area of the big sector AOE equals to pi, and 2 plus square root of 2 squared is 2 squared, that is 4, plus square root of 2 squared, that is 2, plus 2 times square root of 2 divided by 8. So the area of the quarter circle will be equal to pi. Inside the brackets we have 4 plus 2, that is 6, plus 2 times 2 is 4. So in total, this expression in the numerator equals to 4 times square root of 2 divided by 8. Here we divided both the numerator and the denominator of this expression by 2, and actually found out that here we have pi it is equals to pi, and 6 over 2 is 3, and 4 over 2 is 2, so in total inside the brackets you will have 3 plus 2 times square root of 2. So the area of sector, the big sector AOE equals to pi. Inside the brackets we have 3 plus 2 times square root of 2 after we divided both the numerator and the denominator by 2, and we divided the denominator also by 2. The denominator was 8, 8 over 2 is 4. So in total, the area of the big sector AOE equals to pi times 3 plus 2 times root of 2 over 4 square units. Again, the area of this green shape equals to the area of sector AOE is equals to this expression, and we have to subtract from the area of sector AOE the area of this semicircle, and we also have to subtract the area of this green shape BHO. In the next step, we have to find out the area of this semicircle, OBE. We know that the area of any semicircle equals to the area of the circle over 2. The area of this small circle equals to pi r squared, and if we divide the area by 2, we get the area of the semicircle. And we want, it is given us the equation that the radius r of this small semicircle is equals to square root of 2. Therefore, r squared is square root of 2 squared over 2. So the area of the semicircle equals to pi times square root of 2 squared over 2. Square root of 2 squared is 2, so in the numerator we have pi times 2 divided by 2. 2 over 2 is 1, so we left only with pi. In conclusion, found out that the area of this small semicircle equals to pi square units. And we have to subtract from the area of sector AOE the area of this orange shape BHO. What is the area of the orange shape BHO? From the drawing it is very easy to see that the area of the orange shape BHO will be equal to the area of triangle BFO minus the area of the small sector HBF. Again, the area of triangle BFO minus the area of the small sector BFO must be equal to the area of the orange shape. Repeat again, the area of the orange shape BHO equals to the area of triangle BFO minus the area of the small sector BFH. The small sector BFH belongs to the small triangle, to the small circle, to this small circle. Okay, so what is the area of any triangle? The area of any triangle equals to the base of the triangle times the height to the base over 2. So the base and the height are both equal to the square root of 2. So it is the base times the height is square root of 2 times square root of 2 divided by 2. Square root of 2 times square root of 2 is 2, and 2 over 2 is 1. So in conclusion, found out that the area of this triangle BFO is equals to 1 square units minus the area of the small sector BFH. What is the area of the small sector BFH? It will be equal to the area of the small circle, that is pi r squared, times the angle between the legs of this sector that is 45 degrees over 360 degrees. So the area of the small sector BFH will be equal to pi r squared times the angle between the legs of the sector that is 45 degrees over 360 degrees. It is given us the question that r equals to the square root of 2, therefore r squared equals to the square root of 2 squared. So pi r squared is pi times square root of 2 squared, and 45 degrees over 360 degrees is 1 over 8. So in total, this expression equals to pi times square root of 2 squared over 8. Square root of 2 squared is 2. So in total, this expression equals to pi times 2 over 8. Here we divided both the numerator and the denominator of this expression by 2. So 2 pi times 2 is pi, and 8 over 2 is 4. So conclusion found out that the area of the small sector BF8 equals to pi over 4. And we already found out that the area of triangle BFO equals to 1. So in total, the area of the orange shape equals to 1 minus pi over 4 square units. And what is the size of this green shape? The size of this green shape equals to the area of the big sector AOE minus the area of this semicircle minus the area of this orange shape. Repeat again. The value of the shaded area equals to the area of sector AOE, that is equals to this expression, minus the area of the small semicircle, that is pi, minus the area of the green shape, that is equals to 1 minus pi over 4 square units. Here we open the brackets and found out that the value of the shaded area equals to pi times 3 plus 2 times square root of 2 over 4 minus pi, and after we open the brackets we have here minus 1, and minus times minus is plus, so it is minus 1 plus pi over 4. So in conclusion we found out that the value of the shaded area equals to pi times 3 plus 2 times root of 2 over 4, and here we have minus pi plus pi over 4 is minus 3/4 pi minus 1. So here we open the brackets, pi times 3 is 3 pi, and 2 times root of 2 times pi is 2 times root of 2 times pi, and we have here minus 3 pi, and we multiplied minus 1 by 4, and then we divided by 4 in order to a common factor with the other two expressions. So we found out that here we have 3 pi minus 3 pi is 0. So we cancel those two expressions. We left only with 2 times root of 2 pi minus 4 over 4. Here we divided both the numerator and the denominator of this expression by 2. So 2 times root of 2 pi over 2 is root of 2 times pi, and minus 4 over 2 is minus 2. And the denominator we have 4, and 4 over 2 is 2. So in conclusion we found out that the size of this green shape is equals to either square root of 2 times pi minus 2 over 2 square units, or in terms of numbers, the size of this green area equals to 1.2214 square units. Okay, thank you very much.